Hello guys, today we're going to be covering chapter 4 about applications of derivatives. Well, sort of, we're starting that chapter today, but really we're going to do section 4.1, which is maximum and minimum values. So what we're doing is just more application of derivatives. We kind of learn the language of them, like the grammar rules, but now we need to build like sentences off them. Meaning just like, great, now we know how to take derivatives, but what are they used for? How can we actually do something nice with them? So some of the most important applications of differentiation are optimization problems. If you want to like for example, a company may produce a product that requires a special container. So just like, I don't know, just like some weird shape that, something very specific. And you need to package it. But you also, don't want to waste your resources creating really big boxes. But you also want to be able to put the thing in there. So you want to maximize, you want to minimize how much stuff you have to use in order to minimize the product. So, a special container, they'll want the box to cost the least for them to produce. So how can they figure out the dimensions? So the idea is, you have something that you want to minimize or maximize. So you want to maximize profits, minimize costs of things. So to do these kind of problems, we talk about like minimum, maximum values. So, if we look at the graph right here, I forgot to, kind of erase things before I came back around. But if you look at the graph here, this is y is equal to f of x. This will be f of 3, 4. This will be, f of 1, 1. So f of 1, which is equal to 1. So what that tells us is that, when we look at the graph here, what we see is this point right here, this hump, is going to be is the highest point on the graph, and this point right here is going to be the lowest point. So what I mean by f of 1 is okay, what that just means is it exists on the graph. It's okay. It actually exists. So for all x such that, f of x exists, basically that just means is again, this means for all x. So basically just, the x is in the domain. If you choose any other points on this graph, these are all correspond to f of x values. You have f of 1 is less than or equal to f of x for all those x's. That's what it means to be a minimum. It's you want to be smaller than other things around you. Sometimes it can be all things, sometimes it can be lower things. And likewise, we can do the same thing with largest value. Largest value will be, f of 3 is equal to 4, so x value 3, y value 4. And the smallest value is f of 1. So, f of 1 is equal to 1. So basically what I just said. So the fact is that, f of 3 is greater than all the other points on the graph. And at 1, which is going to be, this point right here, typically when we say maximum or minimum values, this refers to the y value. So this shouldn't be 3 right here, this should be 4. So 4 is going to be the absolute max of f, and 1 is going to be the absolute minimum of f. So basically it tells us that the function can take, the highest point of the function is going to be 4, and the lowest point of the function is just going to be 1. It's kind of like what you expect to see from maximum and minimum values. I think you guys have probably seen this before, so I'm not going to worry too much about it, making sure you guys understand it. So, in order for us to kind of be more specific, in order to actually talk about things in a meaningful way, we need a definition. So let C be a number in the domain D of a function f. So it just means just D is just a domain. It's just what we can plug into f really. Then f of c is the f of c is just going to be referred to as just the arbitrary number we want to kind of study. So f of c is an absolute maximum value of f on D if f of c is greater than or equal to f of x for all x and D. So basically it just means in the domain of f of c is going to be greater than or equal to all the other values of f. Likewise for the absolute minimum value of f on D, it's called that if f of c is less than or equal to f of x for all x and D. So basically this is just D is just a domain. So all that really means here is just whatever values you plug in into f, that they'll always be less than or equal to like the maximum. Or likewise, if for all the values you plug into f, so it's like for all x such that f of x exists, meaning it's in the domain, we have that f of c is going to be smaller than all the other x values. This is what it means to be like a minimum. And the fact is that we have for all x such that f of x exists, which is basically just a fancy way of saying x in the domain of f. That's referred to as an absolute minimum because it covers everything we could plug into f. So we also have a sense of like other different languages that we use, which kind of depend on like the context, such as if you're doing differential equations, if you're doing like functional analysis, maybe if you're doing engineering. I'm not sure what the engineering words would be, but sometimes we call them global max or mins, because typically when you say absolute max or min, that could refer to as just like a small compact subset. But when you say global, typically you mean like infinity. Like you go from negative infinity to infinity, and that's like the domains you could plug in. The maximum min values of f, so the max and mins, are also called extreme values of f, and also referred to as extrema. Because sometimes you want to talk about, the fact that they're max and min, but without specifying, which one they are. So it's easy just to say extrema, that way instead of, because sometimes you don't really need to be specific, and you'll see what I mean as we do more examples. All right, so ignore this funky jazz again. So let's just say, again, we have, y is equal to f of x, and this is going to be our curve. So in this case, there is no global max or min, no absolute max or min, because this is going to keep on going to infinity. So it doesn't matter which y value you hit, you'll hit all of them. And likewise, when you go to, you'll have no minimum because this will go down to negative infinity. So the range of this is going to be negative infinity to infinity. And because of that, we have no global max or mins. So there is no global max or min because the function grows unbounded as x goes from positive to negative infinity. And that's basically, again, what it means is that, this is going to keep on decreasing. It's never going to stop decreasing. Likewise, that will always keep on increasing. However, if we look at, 3 and 7, we kind of see that they're absolute max and mins in some case. And we would have some idea that we would want to put some labeling on that. So we can, however, talk about those points as minimum, maximum values locally. Locally meaning, just kind of in some neighborhood, which I'll talk about in just a specific more of what I mean. So near x is equal to 3, we have f of 3 is less than or equal to f of x. And near x equal to 7, we have f of 7 is greater than or equal to f of x. So these minimum maximum values are so these are local max or mins. Or you could say minimum maximum values locally. Typically you just say local max or mins. That's be the preferred language, but we'll go over that in a second. So the reason for this is that if we look at 3, the only thing we need to be in an absolute value, well, an absolute max or min, or absolute, max or min, yeah. The only thing we need is just we need a domain. So really, if we look at 3, for example, if we look at just, this area, forget everything else outside of it, we just look at this area. So, look at everything between these two curves. And if we look at that, we see that 3 will be an absolute minimum there. And because of that, that's how you get the local max or mins. Likewise with, when x is equal to 7, the only thing we need to be able to do is just draw those lines that kind of tell us some area, such that, we can create, y is equal to f of 7 to be a absolute maximum value. So basically, again, just local means, so local max or min let's say you basically can just draw, some section. You could draw a neighborhood. You can draw a circle. I'll just say draw a circle because a circle is technically how we define these things. So you draw a circle around, a value, and it becomes All right. So, like, what that just means is that, like, again, the only thing is, especially when it comes, like, anytime you hear the word local, it just means you should be able to draw a circle or, like, some neighborhood around the point. Typically, these circles are referred to as neighborhoods, but basically it just means you can draw a circle around a point where you have the desired properties. All right. So let's kind of go with the definition of them now. The number f of c, for some function f and for some number c, is called a local maximum value of f. So local max value of f. If the same thing with the absolute maximum value, if f of c is greater than or equal to f of x, when x is near c. And the fact that it is, again, near is a bit vague, but basically just means we could choose a sufficiently small neighborhood or like sufficiently small circle such that it's true. Same thing with the local minimum value of f. If f of c is less than or equal to f of x when x is near c, basically it just means you can draw those lines. We could draw a circle around those points, and it becomes like an absolute maximum in that circle. So we should note that not all functions are going to have extreme values. For example, let's just look at y equals to x. It doesn't have any values that satisfy either definition, because it's always going to be increasing. And because of that, like, it will never have a minimum because it's going to keep on going to infinity. And it's never going to have a maximum because it's always going to go to, like, if we never have a minimum because it goes down to negative infinity, and never has a maximum because it goes to positive infinity. And one of the things I just want to mention real quick, one of the things that kind of determines these properties is the fact that this is on R. So this is an open set. Technically, it's open and closed, but we don't have to worry about it just yet. It is open. So the fact is that we have these parentheses right here, and that kind of dictates the fact that we don't have a maximum. And typically, if you have a setting like this, if you have a closed interval like this, then you might have an absolute maximum. So it's like, how can we determine if a function has any extrema, and if it does, how can we locate where they are? So the first things first is, we need something to say, does it exist? If we don't know something exists, why are we gonna waste our time finding it? Like Bigfoot, like there's like Bigfoot proof such as, footprints or something like that, but if we've never seen the creature, why bother looking for it? So this is kind of where the extreme value theorem kind of comes in. Man, this is going to look funky for you guys, but I'll explain as I go. Let me go back to, let me use orange. All right. So the extreme value theorem. So if f is a continuous function, so continuous function. Okay, I'm lied, I'm dumb. It just says it already. So if f is continuous on a closed interval ab, then f attains an absolute maximum value f of c and an absolute minimum value f of d for some number c, d, and ab. So one of the key things about the extreme value theorem is that we need, continuity on a closed interval. So closed meaning it also has to be like this. So closed means like, it contains its endpoints and it has to be bounded in some sense. Like if it has infinity in it, then it doesn't really become closed anymore in a way that's any useful at all. So likewise, we have f contains an absolute maximum minimum value, f of c and f of d for some numbers c and d and ab. So I just drew some examples here. So if you look at, the first one right here, y is equal to f of x, this is similar to the example we had earlier. We saw here that, one of the minimum value was, the left endpoint, and the maximum value was some point in between. So here our c would be the maximum value, that would be our c right there. And our d, which is, the absolute minimum value, would be the endpoint. And then likewise, we could get more into more complicated situations. We could have, y is equal to f of x right here. And let's just say, like, f of c is going to be like, if we look at this right here, we can assume they all have the same point. So you can assume this peak and this peak have the same y value, and these, troughs have the same, y values as well. So what happens is the extreme value theorem guarantees an existence of at least one. It doesn't say like, more than one. It doesn't say it doesn't tell you how many. It just basically says not 0. So the fact is that there can be cases such as here, where y is equal to fx, and we basically have these kind of humping behavior, or humping behavior, but these humps that we can have, two absolute maximums where they correspond to C1 and C2. So we have two values here. And if you look at f of d, we have 3 values here. So the extreme value theorem guarantees the existence of at least, one of those values, but it's possible we can have more. And that's okay too. It just says, it attains an absolute maximum or minimum. It doesn't tell you how many times, it just said there exists at least one case. So just know that that can be expected too. So again, kind of like what the note says, the note theorem says an absolute maximum must exist, but not that there's only one of each. So if again we look at the extreme value theorem hypothesis, we have that, f is continuous on a closed interval, so we need continuity and we need a closed interval. So if we don't have either of those, then we cannot use the extreme value theorem. Specifically, like one of the things about math theorems is that we have no more or no less than what we need. So if we dropped anything of the hypothesis, if we drop continuity, if we drop a closed interval, then it might not be true anymore. And we don't add any extra assertions that we have not used. There's a joke in whenever we do proofs in my classes. So whenever we prove these kind of theorems, it's like if you have a problem and if you want to prove something and you don't use a part of the hypothesis, you've done it wrong. So everything there is required, and there's very specific reasons why they're required. So like if a function is not continuous on the closed interval AB, so it's not continuous on a closed interval, then it may not have any extreme values. And again, it doesn't even need to be closed. I mean, if it's not closed again, then, it might not have it. So let's just do some examples. So the first example is we have just something on the closed interval 1, 3. We have, f of 3 is equal to 0, so it looks like an absolute minimum. But, if we look at, like just 2 right here, we have an open circle, which refers to as just like, the point there doesn't actually exist. So because of that, we could basically create a sequence of points that get closer and closer, but there would be no maximum. We could always find a point that's higher than it. So because of this, we have no absolute maximum on the interval 1, 3, even though we do have an absolute minimum, we have that, f is not continuous there. Well, and the reason why this is true is because f is not continuous. So this is a case where we do have a closed interval, but we don't have continuity, so it doesn't hold. So remember, the extreme value theorem guarantees the existence of the absolute min and absolute max. So if we don't have them, we don't need to necessarily have all the things we want. And then we could do another example, kind of like where we could do an open interval instead. So let's just assume, g of x is a continuous function and looks like this. So it's easy to see it has an absolute maximum at 1. And, x equals 0, and, g of 1 g of 0 would equal to 1. And then we can see as we get closer and closer to 2, it goes down to negative infinity. So in this case, it would have no vertical, it has a vertical asymptote at 2. And because of that, it has no minimum. And we do have an absolute max, we don't have a minimum, and this is because of the domain of g of x, or like the interval that we're working on, is not closed. So 0, 2 is not closed. If we had 0, 2 like this, then it would be true, but the fact is that it has a vertical asymptote, so it's not going to be true there. So one of the things that we should kind of notice is that when we look at these maximum and values, a lot of times they might be pretty nice. So if you look at this example right here, f of x, y is equal to f of x, assuming f is differentiable, so it's pretty nice. If you look at the the local max here, the local min here, we can kind of see that if it's nice and smooth, then we basically have horizontal tangents. Because basically what's happening here is that the function is decreasing and then the function has to be increasing. So this basically kind of tells us that we should expect at extreme values, like O extrema, that the derivatives there should be equal to 0. Because remember, a horizontal tangent corresponds to having the derivative equal to 0. So if f and c are local extrema, and it basically appears that the tangents are horizontal, i.e. the derivatives there are equal to 0. So this is one of those things that's pretty nice, but it's one of those extra conditions that we can use to kind of classify things. And I'll explain more as we go more into it. So we can talk about Fermat's theorem. So note, not his last theorem, not the thing that took 250 years to prove. It's just Fermat's theorem. So if f has a local maximum or minimum value at c, and we have that f prime of c exists. So given that the fact, it's a local maximum value at c, and the fact that the derivative exists there, then we have f prime of c equals to 0. So we should note that this isn't enough to find, our local extrema. For example, if we take, f of x is equal to x cubed, f of x is equal to x cubed, that way it will kind of look something like this. We'll see that, as we get closer to 0, the derivative at 0, so f prime of x would be equal to 3x squared. F prime of 0 is equal to 0, but we can kind of tell based off the graph that it has no extrema. But there is a horizontal tangent, at x equals 0. So the fact that having just the derivative equal to 0 at some point is not strong enough. It's a requirement, but it's not like, it's necessary, but it's not sufficient. And this is one of those kind of key things we have to understand a lot of times when we do math. Sometimes when we want to just, do something general, like if you just want to find maximum values, we can't really just be super general about it. Sometimes we need to specify some things in order for us to get meaningful results. So Fermat's theorem doesn't count for all possibilities. So if we have, this function right here, y is equal to absolute value of x, then we can kind of see that f of 0 is an absolute minimum, but f prime of 0 does not exist. And we've done that before, that, the absolute value of x is not differentiable at x equals 0 because it's a cusp. So the fact is that Fermat's theorem tells us, requires that f prime of, 0 actually it has to exist, but in this case it doesn't, and we still have an absolute minimum. So one of the key things we've kind of learned so far is that an extrema needs to have f prime of c is equal to 0, or the fact is, f prime of c is undefined. However, that's not enough for something to be an extreme value. It's pretty nice, but it's not exactly it's not exactly one of the things that we need to have. So in certain situations it's true and it will tell us some information, but it's not guaranteed. But again, it's still helpful, and it still gives us at least a place to start. So we got to do some definitions. So let's define a critical number of a function f. So a critical number of a function f is a number c in the domain of f. So basically f of c exists such that f prime of c is equal to 0 or f prime of c does not exist. So basically it's we want to kind of understand that maximum values are going to be critical numbers, but critical numbers are not max or minimum values necessarily. So let's just do an example. So remember that a critical number c is going to be when the derivative is equal to 0 or the derivative does not exist. So let's do an example real quick. So let's find the critical numbers of f of x is equal to x minus 1 divided by x squared plus 4. So f prime of x would be equal to, low d high, so x squared plus 4 times high d low, low d high. So it would be x squared plus 4 times the derivative of x minus 1 is just 1 minus high, so minus x minus 1 times the derivative of low, so 2x, all over low squared. And then all I did here is just, simplify, and you get x squared plus 4 minus 2x squared plus 2x. These will cancel. Well, these will end up being just, x squared minus 2x minus 4. You can pull out the negative, and that'll be your f prime of x. So again, critical numbers are numbers such that the derivative is equal to 0 or does not exist. In this case, x squared plus 4 squared, that's always going to be greater than 0. so we don't really have to worry about it. We don't have to worry about when the derivative doesn't exist, only when it's equal to 0. So we need f prime of x equal to 0. A rational function is only equal to 0 if the numerator is equal to 0. So we just set, x squared minus 2x minus 4 equal to 0, solve for x, and we get x is equal to plus or minus root 5. All you have to do is just plug use the quadratic formula, so we get the critical numbers are plus or minus square root of 5. So again, all we did was take a derivative, find f prime of x, and then find the numbers such that f prime of x is equal to 0. So we can now restate Fermat's theorem with critical numbers, because the critical number again was when the derivative is equal to 0 or whenever it doesn't exist. So this is a slightly stronger version of it, but this is the way you would want to remember it. So this is a more important one. So if f has a local maximum min value at c, then f is a critical number of f, or f is a critical, c is a critical number of f. So the derivative there exists and it's equal to 0, or just doesn't exist. So we have this thing called the closed interval method, which allows us to identify, maximum min values pretty nicely. So it's basically kind of like an algorithm that basically allows us to find absolute max and absolute min values of a constant function, or not constant, of a continuous function on a closed interval AB. So we should note that we have continuous and we have closed interval, so that basically means extreme value theorem. And using Fermat's theorem, basically can kind of tell us about what we can do on the inside. So continuous and closed interval basically says by extreme value theorem is that absolute maximums exist, but we don't know how to find them. So now we can say we're basically not wasting our time. So the closed interval method is how we find these. So the first step would be to find the values of f, find the values of f at the critical numbers of f in AB. So we find all the critical numbers of f, we set the derivative equal to 0, and we set it equal to AB. Well, we set the derivative equal to 0, or we find out the places where it doesn't exist, because that's going to be a maximum or minimum value. And then the next thing we do is we find the values of the endpoints of the interval, and then the largest value from the step 1, and step 2 is going to be the absolute maximum, and the smallest of these is the absolute minimum. So this may seem kind of weird, but basically the idea is Fermat's theorem, is f is a local maximum min value at c, but if we take a case basically tells us, a local maximum min basically occurs, whenever we have a cusp or something like that. But let's just say we consider a function like this, but we only define it to be in this area. So while yes, these are, local max or mins, but the max and mins here are going to be occurring on the endpoints. In those cases, the derivative is not going to be equal to 0, and it's still going to be defined there. So the derivative there would actually be it doesn't have to be 0. It could be 7 or 11 or negative 32, but and it still wouldn't be a local max or min. But the fact is that it could be the endpoints as well. And that's what this kind of idea is. We find the local max or mins, we check the endpoints just in case, the endpoints are higher or lower than those values. So that's an example. I realized when I wrote this the first time, I actually wrote something double. So you want to find the absolute maximum and the absolute minimum values of f of x is equal to 5 plus 54x minus 2x cubed on the interval 0, 4. So what we're going to be doing here is just an example of how we use the closed interval, method. So let me just kind of erase this as I go. I realize I should have done it beforehand, so I apologize. But again, so we have a continuous function because polynomials are continuous, and we have a closed interval. So actually, it's kind of what I said right here. F is continuous on a closed interval, so we can use the closed interval method. So the extreme value theorem basically says these things exist, but we need to find them. So step 1, which is going to be find the values of the critical points of f in 0, 4. And remember that this is, in the open interval. This does not include the endpoints. So the first thing we need to do is find the critical points of f in 0, 4. So we take a derivative, we get f prime of x is equal to negative 6x squared plus 54. And then we need the critical number, so we set it equal to 0. We get negative 6x squared plus 54 equal to 0. Take out the negative 6, divide by it. We get x squared minus 9 equal to 0. So we get x plus 3 or x minus 3 is equal to 0. So we get x is equal to plus or minus 3. But we need the x's to be, in 0, 4, so we can disregard the negative. So, x is equal to 3 is going to be our critical number. Our only critical number in 0, 4, and the value of f of 3 is going to be, just 113. And the next step after that would be we find the values of f at the endpoints. So at the endpoints, we get, 0, 4. So we get 0 and 4 as the points we need to plug in. So we get f of 0 is equal to 5. And f of 4 is going to equal to 93. And the next step we're going to do is we compare the values to determine absolute max and mins of, of the function. So we have, f of 0 is equal to 5, f of 4 is equal to 93. That comes from the endpoints, and f of 3 is equal to 113. That comes from a critical number. So we have that, f of 3 is equal to 113, f of 0 is equal to 5, and f of 4 is equal to 93. Thus, it follows that 113, which is the greatest value of these, is going to, equal to f of 3 is going to be the absolute maximum, and f of 0, which is equal to 5, is the absolute minimum. So basically what this tells us is that, we compared all the other cases, we look at all the options, the smallest number is going to be 5, so that's going to be our absolute minimum, and the biggest number is 113, so that's going to be our absolute maximum. And this right here is like a list of possible cases why we have to do such intensive testing. So we can have cases where, I'm just going to assume this is just, 0, 4. So in the case that we have right here, we had, f of 0 is going to be our maximum. So it was right around here. Well, f of 0 is equal to 5 is going to be our absolute minimum. And then we had that, we had a maximum at 113. But then at f of 4, it was 93. So this could be a case where it's where we have, the minimum occurs on the boundary or on the endpoints, and the maximum occurs on the top of it, where the maximum occurs somewhere in between 0 and 4. It's possible that, that the maximum only occurs, the maximum ends only occurs on the boundary and you have no critical numbers. And it's possible that, you could have critical numbers and those would be the only maximums you have. So in this case is right here. So it's kind of we have to account for all these steps in order to get all the absolute maximums, because there's many different cases that we could have. But, that's it for this section. This stuff is a bit, it's not too complicated, but you just have to know that, you have to be able to appeal to theorems, especially the extreme value theorem is pretty important. Just knowing the fact that, if it's continuous in a closed interval, then you have an absolute max and min. And that critical numbers are basically where is going to be those local max or mins. And those really help you, try to figure where those are out. But thank you for watching. Like, comment, and subscribe. Hope you guys enjoyed the video.